Students, so what I would like to do is to just take you through in a step-by-step manner this tutorial paper, which consists of some typical exam type questions. For example, the first question asks us to explain what is meant by the terms open system, closed system, and isolated system. Now, open system is one which can exchange both matter and energy with its surroundings. An example of that is, for example, let's say a beaker. Let's say you have a beaker. Let me just put this back. Let's get this writing device. Let's say you have a beaker, right? And you have a reaction taking place in that beaker, which is producing a gas. So if you have a reaction taking place that is producing a gas, then of course the gas would escape. This is your gas escaping. So that's an open system. It is exchanging both matter, and it can also exchange energy with its surroundings. Let's say, for example, heat energy can be exchanged with its surroundings. On the other hand, for a closed system, right, a closed system can exchange only energy but not matter with its surroundings. So again, you could use something like, if you want, you could use a beaker or a sealed vessel, right? A sealed vessel. So let's say it contains some particles, right? These particles cannot escape. However, heat energy can escape, or energy overall. Let's just put it generally and say energy can be exchanged with its surroundings. Energy can also be going in to the system, okay? And that is a closed system. An isolated system, let me just get this off. An isolated system is one that does not exchange anything with its surroundings. That is, it does not exchange energy or matter with its surroundings. And a special case of that is an adiabatic system. An adiabatic system is a special case of an isolated system. So nothing is exchanged with its surroundings. Now, this other question is asking us to prove that for a chemical system, the work done when a gaseous product and or reactants are involved is given by minus P delta V. So we have to prove that the chemical system, right, that for a chemical system, the work done, right, when gases are involved is equal to minus P delta V. Okay, let's see if we can do that. Let's say we have a cylinder, okay? And there's a movable piston in the cylinder. Let's see if I could draw a piston. Have a piston there, or a cover if you want to call it that. And there is a pressure pushing down on that cover. That pressure is the external pressure, Ex, due to the atmosphere. The weight of the molecules in the atmosphere will be pushing down on that cover. Okay, let's say the cylinder is a little bit longer. All right. Now, if there is a reaction taking place in this vessel, and this reaction, let's say the reaction starts out with 3 moles of gaseous reactants, okay? Let's say gas. And then, as the reaction is proceeding, it produces, let's say, this cylinder is looking a little bit too big. Let me just fix that. All right, let's see if we can make it similar in size to the previous cylinder. All right, so we don't get too worried. Okay, let's see. Okay, something like that. Something like that. Okay. Let's say the reaction produces, let's say, 5 moles of gas. All right. Now, of course, if you have more gas particles, then the cover or the piston, if you want to call it that, would travel some distance upwards. Okay, because you have more gas particles. According to Avogadro's law, the number of gas particles is proportional to the volume occupied given that temperature and pressure are constant. That's Avogadro's law. That's what Avogadro says. So the distance traveled by this cover or piston, let's call this H final, and let's call this H initial, which will be the initial height. So the distance traveled D is equal to H final minus H initial, or you could say delta H. Okay? All right, that is clear. Now, remember, pressure, pressure, right? For example, the external pressure is equal to what? It's equal to force, all right, over area. It's a ratio of force to area, force applied per unit area. Now you could rearrange this formula a little bit and, basically to make force the subject. So force is equal to pressure times area, EA. Okay, good. Why are we doing this? Remember, work is equal to force times distance. Okay? So what we could do with this formula is to write instead work is equal to PA, which is the same thing as saying force. PA, pressure times area, is equal to force, right? Times distance. Okay? Pressure times area is equal to distance. Now, this distance will affect something. This change in the position of the piston will affect the volume of the cylinder. Okay? Yes, look at this. The volume, I'm sure you would agree, the volume would have increased, right? The volume would have increased because now you have more gas particles. The piston is further up, and so the volume would have increased. Now, we must recall something else. Remember from our basic mathematics where we were calculating volumes of three-dimensional objects, we know that the cross-sectional area of an object times its length, all right, times its length or height, which is like the distance, is equal to its volume. If there is going to be a change in the, matter of fact, let's change this D here and call it L. Let's call this L. Okay, let's call it L. Let's call this L instead of D. So the volume of a three-dimensional object is equal to cross-sectional area times its length. Okay. For our system, there was a change. There was a change in the volume of the system. So now we have to write delta V, change in volume, is due to a change in the length. That change in the length is called D. It is the distance traveled by the cover or by the piston. Okay? All right. So we could rearrange this formula to make D the subject. All right, let's rearrange this formula here to make D the subject. Here we go. Delta V divided by A is equal to D. D is the distance traveled by the cover. D is basically the increase in the length of the cylinder, which resulted in an increase in the volume of the cylinder. Now, seeing that we have an expression for D, what we could do is to take this expression and plug it into this formula here. Okay, so look at what we're going to do now. Work is equal to pressure, all right, times area times change in volume over area. Area will cancel with area, right? And so what we have now is that work is equal to P delta V. If we say that work is being done by the system, if we assume that the system is the one always doing the work, then we put a minus sign. All right? Now you're probably saying, how could you just make such an assumption? How come you're just making such an assumption to, that the system is always doing work? Yes, it's a convention given to you, but it works. Why? Because if work was done on the system and the piston or the cover had moved downward instead, then the volume change would have been negative, and so this negative sign would have been cancelled away, indicating that work was done on the system. Okay? So that is how that works. That is how that works. Okay? All right. Now, this other calculation asks us to calculate the work done when 1 mole of propane reacts stoichiometrically with oxygen, right, to give carbon dioxide gas and steam, right, which is gaseous water, at 1 atmosphere and 25 degrees Celsius. All right, maybe the first thing one should do is to try to write the equation. Propane, I do believe, is C3H, 2 times 3 is 6 plus 2 is 8, right? Plus oxygen gas, so it's propane gas reacting with oxygen gas to give you your steam, yes, plus carbon dioxide gas. Now we need to balance this. Looks to me we need to put a 3 there. Okay, so because we have 3 carbons over here, we want to also have 3 carbons over there. Makes a little bit of sense. Okay, in terms of the hydrogens, we have 8 hydrogens here, and so we want 8 over this side, so maybe we should put a 4 there. Okay, now we have a problem with our oxygens because we only have 2 atoms of oxygen over here, which 2 atoms come together to make 1 oxygen molecule. But over here, we have what? 4 times 1, that's 4. 3 times 2, that's 6. So that's 10 total oxygens on the product side. So it seems to me we probably need to put a 5 here to balance this equation. This is what we have. Okay, so we're supposed to calculate the work done when 1 mole of propane reacts stoichiometrically with oxygen to give carbon dioxide and steam at 1 atmosphere and 25 degrees Celsius. Of course, you're probably wondering, well, how can I calculate the work if work is given by minus P delta V? That is, yes, that is a little bit of a challenge, not an insurmountable challenge, but it's a little bit of a challenge. Indeed, you could still calculate the volume change by assuming ideal gas conditions, but there's an easier way. Remember this: PV, yes, is equal to nRE. Okay, so P delta V must be equal to some change on this side, which could be delta N R T. Okay, R is a constant and T is a constant given to us as 25 degrees Celsius. So you could use this formula. So work, what I'm saying is work is equal to minus P delta V, which is also equal to minus delta N R T. What is this delta N though? What is this delta N? What does delta N mean? Delta N is the number of moles of gaseous products minus number of moles of gaseous reactants. How does that work? Okay, let's try it. Let's try it. Okay, number of moles of gaseous products is 4 moles of steam, which is gas, and 3 moles of carbon dioxide gas. 4 plus 3, that's 7. So it's 7 minus, okay, number of moles of gaseous reactants, 5 moles of oxygen gas, plus 1 mole of propane gas. Okay, 1 plus 5 is 6. So our delta N turns out to be 1. Okay? All right, let's go through the calculations now. Let's go through this calculation. Work is equal to, right, minus, and I'll just put this back down here. I'll just put this calculation back down here. 7 minus 6, right? And this is mole times 8.314 joules per Kelvin per mole. And we always include our units. We always include our units in our calculations so we can see how they cancel out. And then also now our temperature, it is about 298.2 Kelvin. Kelvin here, we'll cancel with that one. Mole here, reciprocal mole I should say, we'll cancel with this mole here. Okay, let's see. Work is then equal to, let's get our calculators. All right, got my calculator. So it's minus, yes, minus bracket 7 minus 6 bracket times 8.314, yes, times 2. To be careful how we put these in our calculators, 298.15. I got something like, let's see what I got. Let's write down what I have here. I have minus 247 right. Right, so what I have is minus 2478.82 joules. Let me just check that again, right? Because we're always rechecking our calculations, always. All right, 7 minus 6, right? We know that is 1, and we have to include the minus sign there, which is naturally a part of the formula. 8.314 which is the universal gas constant, times 298.15. Okay, and I got 2478.819, and I rounded up to 82. All right, 0.82. Okay, so that's what I got for that one. That is the work for this system. Okay, let's try another question. It says this question, part B, right? It's B, part B. It says the enthalpy change for this reaction is, and I guess it's referring to the reaction from part A, is 2043 kilojoules per mole. Calculate the value of delta U and delta H at 1 atmosphere and 25 degrees Celsius. All right, let's see if we can do that. Now, delta U, all right, remember what delta U is equal to according to the first law of thermodynamics. Delta U is equal to Q plus W. All right, where W is the work and Q is the heat change. All right, delta U then is equal to, the heat is given to us here, enthalpy of the reaction at constant, heat of the reaction at constant pressure, which is the enthalpy. All right, so because the pressure is constant, here it is 1 atmosphere, and so the enthalpy is equal to the heat, right? That's a simple definition for enthalpy, right? It is the heat change at constant pressure. Okay, that's a simple definition. All right, so I'll put it here, put my heat here, 20, and I put times 10 to the 3. This is me converting to joules. All right, and that is important, that all your values are, of the same magnitude in terms of their units. Also, now I'm going to add to this the work plus the work that we calculated earlier, I believe, is 2,478.82. All right, and it was minus, don't forget that, minus, and it was in joules. Okay, now at the end of the day, let's just calculate the actual value for delta U. Let me see if I can do that. Minus, okay, you have to make sure you plug these in correctly in your calculator. Okay, this is what I got, and you should just check to see that my value is a good value. All right, 2045 joules. 2045 joules. Now, what lessons can you take away from this? The, what you should notice is that the hold it 2045. Yes, this should be kilojoules. Sorry, kilojoules. Okay, because I converted back to kilojoules after this, right? If you want the actual value, we could actually write it out. As a matter of fact, let's write it out. Let's write that value out, just so we don't, lose our way. Let's just write that value out and then convert to kilojoules. Okay, let's not take any shortcuts. So it's times 10 to the 3 joules, which is kilojoules. All right, kilojoules, and it is minus. Don't forget that. All right, that is critical. Now, what lessons can we take from this? Look at the size of this value, the size of the internal energy value, and look how similar it is to the enthalpy or the heat change of the reaction. It's almost the same. Not identical, but it's very similar. What this tells you is that the contribution of work to internal energy is very small. It is really the heat change, Q, which is the dominant factor. It is the dominant factor that determines the size of the internal energy change and not the work. I'm not saying that the work is not important. I'm not saying that. What I'm saying is, out of these two factors, Q is more influential. Q controls or has a greater say in the size of the internal energy change than the work. Okay? Right. All right, so the work component is generally small compared to Q. Let's try something else. Now we are being asked to sketch an appropriate energy profile diagram. Let's see, did we complete that question? I think we forgot to add something. We forgot to calculate delta H. We calculated delta U but did not calculate delta H. We have to be careful. All right. This is interesting because things like this happens all the time on exams. So it's a good thing we made this error to point this out and be careful. Okay. So we need to calculate delta H as well. What is delta H equal to? Well, remember this. Delta H, right, which is the enthalpy change, is equal to the change in the internal energy, right, plus P delta V. All right, don't forget this. Okay, so that is how you would calculate it. Now remember wherever there is P delta V, you could always replace it with delta nRT. Don't forget that. So what I am saying then is that you could write delta H is equal to delta U plus delta nRT. Yeah, don't forget that. All right, let's try it. Let's calculate it. Let's calculate. Let's try to calculate this. Well, we have delta U, we know that. So it's 2.45, yes, times 10 to the 3. I'm just putting it in joules, all right? Plus delta nRT. We actually have that value already. Let's go back and have a look at it. The work value is minus 2,478.82. That's right. And this is the positive of it. 2,478, 2,478.82 joules. Okay? That's what it works out to be. All right, and it's a positive of it. There's a positive, yeah. So, what is the answer? Let us erase some of this from the top and put our answer down. Let's erase some of this. Getting a little bit crowded. All right. Okay. Almost there. All right. So, let's just calculate this value. Let us calculate this value. Delta H is equal to, let me just get my calculator. And I have a value of, let's see what I have here. Wow, very interesting. Very interesting. And this is times 10 to the 3 joules. Let me also put it in kilojoules. What do you know? This value is basically the same value, right? It's the same value used up here. You see? The enthalpy change. Huh? Interesting. Very interesting. Now, we use this value as Q. Earlier when we were calculating delta U, we used this value as Q. This proves now that also that Q at constant pressure is the same thing as the enthalpy change. Okay, it's the same value. A matter of fact, in the question, maybe we could have actually put, Q instead. All right, I'll say that the heat change for the reaction is minus 2043 kilojoules per mole. We could have done that. Okay, but anyway, we got it. Look at this other part of the question, which is asking us to sketch an appropriate energy profile diagram to represent the reaction outlined in A. I wonder what that looks like. Okay, well, look at the enthalpy change value. It is negative. That tells you it's an exothermic reaction. So we know what we should be looking for. For exothermic reaction, heat energy is released, all right? The net process involves the release of heat energy. So what you'll have is a situation where the reactants are higher in energy than the products. Yeah, of course, you have to have an activation barrier. All reactions have that. All right. Some reactions, the activation energy barriers are so small that we say, look, it's a barrierless. But all reactions have some sort of activation energy barrier. Okay. Right. So this is our energy profile. You could call this reaction path. And here you could put H, enthalpy. All right. And of course, you have your reactants. You have your reactants. So if it's a reaction where you have A going to give you a product P, then you have A up here, product down here. Right here, you could label this if you want and say this is the activation energy. And then down here, if you want, you could call this the delta H of the reaction. Okay? And that is your energy profile diagram. Okay, so we'll look at other concepts soon. Until then, take care.